Hey, what's going on, guys? Coming here. In this video I'd like to introduce a new project I've just started working on, and it's a sort of a 6502 processor simulator. But in order to describe what the project is all about, I need to first explain the backgrounds I came from and what serves as the inspiration for me currently. So what I've been working on so far, and this project might be treated as a completed one already. So I was making some 16-bit realm mode operating system, kind of like operating system for running boot sector games and apps, where you just have a list. Where you have a list of commands. Where this is the so-called dev pack, so it doesn't actually contain any games, but it could have so instead of the programs, let's say like this help actually runs in a boot sector. If I run some sample programs like prog1, prog2, etc., placeholder, I have a code editor here, so I can type in some code in assembly. I'll demonstrate it just a little bit, just in a moment. But the initial, that's how we could run the apps, right? So whatever of these commands is the boot sector application, and code gets loaded into the boot sector, and once I hit enter, it just starts running there. That's pretty much all about it. And I've been demonstrating how it works with some basic games, like I have even created my own game of Soccer Band for this, and there were some videos. I use some third-party games like Snake or Tetris or even Arkanoid and even Pac-Man by Oscar Toledo. Absolutely out of this world one. But just running the games wasn't that interesting, and I decided, how can I actually set up the very basic development environment? And since this entire operating system is written in x86 assembly, I didn't have any compiler for that. I couldn't use there is no compiler for this system, no C compiler, and like using the C compiler outside of it and then just bring the code in is not interesting, because I was interested in developing exactly under this particular system with no other software dependencies. So the initial attempt was to simply create a code editor like this. Yeah, by the way, just let me reset this. And you can actually run whatever code is available there. Well, I just resetted it, it just doesn't work really. But if I reset the entire system and, for instance, go into the editor and say input the address and then just say EA000008, so this is the command to make a long jump back to the shell, and if I now run, it just successfully returns. So this is one of the simplest programs kind of possible written in machine codes. I've been playing around with this. The most significant thing what I have managed to do using this sort of a technique is creating a matrix screensaver in 44 bytes, which is available as a tutorial on this channel as well. Currently it's a trailer video on the channel, but when you would be watching this, there may be a different trailer. But anyway, so in order to actually compose, in order to turn x86 assembly to machine codes, I've created this lookup tables. So I've been demonstrating, so there was the entire series on how to hand code, to make this handcrafted machine codes. So you just type a line in assembly, then convert this to machine codes. That's pretty much all about it. Then you just put those machine codes into the hex editor and you're done. And even that still seemed to be like a bit too quirky. And eventually the last thing I've achieved there is I've used the third-party, absolutely out of this world assembler, x86 assembler with a very limited instruction set created by Kayhan Vakil. And what it does actually, so if I go to the code editor, yeah, that's another application that just writes bytes into the buffer, into the random access memory. It's at address 1800 if I'm not mistaken. So let's say I can say x or ax, and then let's say just, I don't know, return, for instance. Well, don't want return, let's say I don't know, let's say x or bx. Just some very basic commands here. And then if I say new to clear the editor, and if then I say ASM, if everything works perfectly, it manages to assemble the code. And if I now run this, would actually execute what is written there, just to reset the AX register and reset the BX register. I'm not going to be demonstrating you this because it will stuck and doesn't do anything useful here so far, so nothing really to be talking about. But at this point, I've realized that I don't have a normal assembler, and like coding in machine codes, in x86 machine codes at very least, it's just a bit too much even for me. So, you know, like I felt that I was doing something. So initially I wanted to have a bootable environment capable of running boot sector games. Then I wanted to try and write my own games under this environment and so on. But then I stuck because I didn't see where to develop this project. And then it turned out that I've discovered 6502 assembly language, 6502 assembly programming language for the 6502 MOS 6502 processor of the very early days. I wasn't even born when that processor was actually created. So and since then, since I've tried writing in that assembly in this JavaScript simulator adopted by Nick Morgan, I've realized that it's so cool to write in. This is so cool to write in 6502 assembly. And then I was thinking, what if I try to make my own simulator? Well, obviously, so it's now a bit of a difference in terms like the emulator versus the simulators. So what's the difference? So, well, according to my understanding, so the emulator is something that tries to mimic the real thing, the real hardware in our case. While the simulator is just something that is giving you an experience similar to what you will have on the real hardware, but it's not real. So, well, for instance, in simulator, we can drop such things as the processor ticks, for instance. So how many like ticks it takes to complete the instruction. So also the original frequency of the processor is not taken into account. So like the modern, this one, it kind of runs on the frequency of the actual processor x86 minus JavaScript minus this simulator, but actually it's incredibly bigger as opposed to that 1 megahertz frequency that was used back in the day. However, if it was an emulator like this absolutely fantastic Apple I emulator, which we're already coming to, it actually tried to mimic even the actual, I'm sorry, not 1 megahertz, but 1 megahertz, yeah. All right, so it even tried to mimic this, the actual speed. So it was kind of like an attempt to run the software for Apple I in like the real speed, right? The original speed. So and this computer, this Apple I, I've discovered this just a couple of days ago. I was watching a video by 8-Bit Guy, a very famous YouTuber who specifies like this either homebrewed computers or just very old computers, so like mostly 8-bit computers. And he was soldering his own Apple I and then running it and then just trying some very basic commands from the rare Apple manual, which we have here. And we'll now play around with this. And when I saw how this Apple I back in 1976 was operating, I've realized that what I was trying to do in my game was, without even knowing that Apple I existed. Well, I knew that it existed, but I didn't know anything about it, basically. So when I saw how this actual system works, I've realized that I was trying to make something the same even without realizing that actually exists. And the problem of what I was trying to do so far was the lack of the entire general concept. So what I was trying to use as the entire general concept is just to have this minimalism in terms of the limitation to 512 bytes for a single application or a game, and just to be able to run them. But it turned out that the actual limitations of the so-called development environment were a bit too hardcore, so it's literally impossible, like very impractical to develop. It's technically it's possible to develop under my operating system, like the real game, but from the practical perspective, it's very impractical. So you won't really be doing that actually. So it's more like intended to be coded like outside, like on Linux or on Windows or wherever, and then just loading this assembling, loading the code into the image, and then writing this to the USB flash drive and running on the real hardware, or just running the emulator like I'm doing here. But anyway, so even though it's possible to create some programs from within, still it's very impractical. So this project came to its logical end in terms of I did everything I could do. And initially, again, I had an idea to have some limitations to make it more interesting. And my main limitation was to have this 512 bytes limitation for a binary executable. Now, the 6502 processor has its natural limitations because, first of all, it's 8-bit, then it has only 3 general purpose registers, and coding in it is really limited on its own. So for that case, we don't really need this 512 bytes limitations and things like that. So I decided that just writing in 6502 assembly is already a good enough limitation for 2021 at the very least. And having a very nice experience in this online JavaScript simulator, eventually I took a hard decision trying to implement my very own simulator of 6502 processor, generally using the concept that Apple One actually used. So I'll now demonstrate how in this awesome Apple One.js JavaScript emulator of the old Apple One computer. So what the user could see when he just bought the computer, like plugged in, and the very first keys that he was meant to type from the keyboard. So what the experience, what he would see. I will now demonstrate you that, and hopefully this would give an idea of what am I trying to build next. So without further ado, let's start. So probably, well, I can't say for sure because I've never touched a real Apple One. Not many people did, really. That was a very limited series. So if you watch the movie about the Steve Jobs of 2013, I believe. I've been rewatching that movie yesterday, by the way. So yeah, that's the story of how Steve Wozniak actually created this Apple One. So we need to hit the reset button first, and this is the dreaded command line with the @ symbol instead of the cursor. And here, if we just go to the user manual, so here is the user manual. And what a cool thing about the computers of back in the day, that they all actually have this user manual. By the way, the very initial logo of Apple was like this, featuring Isaac Newton and the apple that kind of hits his head, which not many people know, including me. I just didn't know about this just a week ago, for instance. So yeah, it contains some hardware stuff like how to connect things, which I have no idea about because I'm complete noob in electronics. But here, starting from the very first program, this starts getting interesting. So first, hit the reset button to enter the system monitor. So what we have here, is known as the system monitor, and this is the program that runs in ROM, not in RAM, but in ROM. So RAM is random access memory, and ROM is read-only memory, right? So there is a program which is similar to my hex editor, but it takes, well, my hex editor takes 512 bytes, and this one takes only 256 bytes, but it has fewer features for editing. It doesn't have, you just can't just input line by line, and that's pretty much all about it. So it's not that feature. So in my editor, I could specify the address and, well, probably I can't do a fair comparison because I didn't yet test Apple One that extensively to make this fair comparison. So let's just forget about my previous operating system and switch here. So let's try to input some program. So backslash should appear and the cursor should drop on the next line, which happened. So we have the backslash appear, the cursor on the next line. Pretty awesome. And now type this sort of a thing. So 0 colon 0 colon. Okay, guys, I'm probably I can put this to a new window. Please go to the new window, right? And let's put this one in here. Yeah, it should be faster like this. All right. So 0 colon A9. So I have no idea what this kind of does in particular. So B stands for space, B 0 B A 20 space EF space FF. So it seems like that, yeah, the bytes, there should be spaces between the bytes. Well, doesn't matter really. So EF break FF, now E8. If I did something wrong, I will need to retype this from scratch because it doesn't have the backspace. So E8 break F8 for C 2 0 and hit enter. Okay, third type 0 dot A. This should print the program that you just entered, which it does. So well, it seems like, well, I'm not sure, but it seems like it actually writes the program into the 0 pages, assuming the actual address of the random access memory, because the first 256 bytes are the 0 pages. Well, that's where, at least that's where the 6502 processor is looking for 0 pages when it encounters the instructions involving the 0 page addressing mode. So it's a little bit strange why the program is typed here, but still probably it lets the program counter jump in there, and that's another big topic for this video as well, like how to set the system defaults for a 6502 processor. But anyway, so we see that the code that we just typed in, and then we just need to type R to run the program, and the program should print the continuous stream of ASCII characters, and that's even what was seen in the movie, like that I've been mentioning already. So R and enter, and it does actually. So it actually does print this ASCII characters. So this is how Apple I meant to be programmed. So this absolutely tremendous kind of hex editor, allowing to type in the 6502 machine codes and get some output in return. So and it would actually last forever. So yeah. So also again, in this emulator, it's kind of like simplified things. So in order to load some tape, you don't actually need to type any machine codes. But as I saw in the video by 8-bit guy, he was actually forced to type in some machine commands to like invoke like to listen to the bytes coming from the tape, right? Or I'm not sure if I'm talking some gibberish now, but anyway, so we can actually load some programs just by clicking load and specifying the program. And this is one of the historical programs that actually prints the portrait of Steve Wozniak, the creator of this exact Apple I computer, which wasn't even called like that when he just created it. It was just making this for fun, for his own kind of like pleasure, and that's really awesome. So I believe that this, even though it's called Apple, I think it shouldn't be called like that, because it actually doesn't have any, well, according to I have no idea how this was in the real life, but according to the movie that I've been watching, that this computer was already created when actually Steve Jobs kind of saw it and then started his marketing thing. And yeah, and here it's also print the Steve Jobs as well. So that's yeah, one of the very first, one of the most famous programs like that were originally available on the original Apple I. And I think that back in the day this was really impressive. Well, for me personally, this is impressive even now, because yeah, this is cool. This is really cool. So what can I say? So this sort of an interface that has hex editor in the RAM, and that allows to. I'm not sure if it's gonna last forever, or it's probably. I didn't even watch until this place, so let's have a look. That's probably the Apple logo here. Yeah. So yeah, it even tries to mimic the colors. Oh my god, this is so cool. It even tries to mimic the colors in the original Apple logo. Okay, so what I really like about this computer is the concept. So it's probably the most minimalist thin you could have ever imagined, right? Because it's really kind of like, it's really minimalist, right? And it's very, in its minimalism, it's very tight, and it's very kind of like, so it's completed, it's totally completed, and all the concepts it has behind it, just, I don't know, it just, you don't need to add anything. If you start adding anything else, it just loses its original charm. So I believe that's kind of the thing, right? So I've decided to actually use this Apple One as the source of inspiration, right? So the source of inspiration for creating my own simulator. So I don't call it emulator, and you will now understand why exactly, because it's not intended to do what this amazing Apple One JavaScript emulator does. But instead, I just want to simulate exactly the same behavior that we have here. So I just want to type in 6502 machine codes into the built-in hex editor in order to execute that, right? What else? Also, I want to be able to run some programs that would be hard-coded into the USB flash drive, the image of this kind of like operating system. So I want to make it bootable. So it's going to be written in x86 assembly. I know I've already started the work. I will show you that at the end by the end of this video. So yeah, this is kind of like the source of inspiration. So now, yeah, let's close. Well, actually, we'll still need this manual, so I'm not going to be closing this entirely for now. And now let's go to a bit of a more like technical documentation. So again, I'm complete noob in electronics, so this kind of scheme doesn't tell me much really. But what I've realized so far, that initially it had two RAM slots. I don't know how to call it properly. So 4K and 4K. So totally like 8K RAM at most, and 256 RAM, which is very minimalist. And this kind of like initial hex editor so that allows us to see the blinking cursor, allows us to type in machine codes. All this stuff is stored here. And by the way, in the user manual, down below, we have the listing for this monitor. So you see, like, it's just clears the decimal arithmetical flag, all the stuff. Then it just prints this backslash, okay, and then it just echoes it to the screen, and then it starts listening to the keyboard input. Initialize text index. Yeah, so this is the entire source code in 6502 assembly that actually allows us to type in machine codes and make them run. So this is very awesome, and I'm gonna be making somewhat a similar thing. Well, I'm gonna be using this as the source of inspiration, I believe, but well, probably my implementation won't be that accurate to actually run it natively, so probably I would need some kind of like alternates. But anyway, what is interesting here is this addresses, all right? And you just know that, so this is RAM, so read-only memory. So this is kind of like a hard-coded program that starts working when computer boots, okay? And it starts from the address FF. And the interesting thing here, which is specific to 6502 processor, is, oh my god, is it Han or what? which is specific to 6502 processor, is down below here. So notice this 3 bytes at the end, so non-maskable interrupt, reset, and oh my god, I forgot what this stands for. We'll now see. All right, so the way. So I also heard that it was using the hardware-based teletype mode character echoing system. I'm wondering, is this where it happens actually or not? I'm not sure, but anyway, it doesn't matter much at the moment. So another very important documentation part is the 6502 primer, building your own 6502 computer. So memory map requirements. So this is interesting, which I didn't know about. So the 6502 treats I/O and memory the same. For example, if you have the instruction set the value of accumulator at this particular address, the processor doesn't care if you're storing the accumulator value to RAM or to input-output, not sure what IC stands for, register, or anything else. You would normally want to have your source code specify the name of a variable, input-output register, or whatever, but emphasis here is on the actual address. So, well, for me personally, when I read this, what it reminds to me is the Linux philosophy of everything is file. So let's say on Linux, if you want to write bytes to USB flash drive, that's treated to be as just like yet another location in the file system. So for me personally, this is very similar. Maybe my understanding is horribly wrong, but that's how my noob's mind actually gets that at current point. So occasionally, there are only a couple of relative non-negotiable requirements to keep in mind. Yeah, so only a couple of relatively, non-negotiable. So something that you don't need to ask about why and so on. Well, and most likely I'm not going to be even implementing this because, well, for me it's just like a bit overwhelming complications. But I just want to cover this because, there is a very nice series on YouTube. It's called something like coding a 6502 processor or emulating a processor in C++ by David Poole. That's the name of the guy who has created that. And there was a mistake, which one guy in the commentaries was kind of pissed off about. It's the question of where the program counter starts. So when we're talking about where the stack pointer starts, it's quite pretty clear because it points to the random access memory. But the program counter initially points to the read-only memory, and and lots of confusions are arising because of that. So let me just here it is. So this part about the RAM. So an interesting thing that normally your design will need a RAM in address starting from this address range. Well, actually, it starts not exactly from. Well, that's probably the minimalist, or I don't know. Well, in Apple 1, this starts from FF00, and well, I'm not claiming anything, but just to give you an idea, how did I come up with that sort of a conclusion, right? So here, the hex monitor listing starts FF00, and we know that it takes 256 bytes. And down below we have this FFFE, so the very last byte here, right? So it takes exactly 256 bytes. But what is it really interesting that for some reason the addressing at the RAM, at the read-only memory starts from FF. And for me personally, this is really unclear how on earth is that possible, because if the entire RAM has only 256 bytes, then how on earth the very first address can be like this one? Well, obviously we can easily emulate this by adding a constant of FF00 to the actual address, like in RAM here. So it's not a problem to simulate this, but just physically it's a bit unclear for me how on earth the address in RAM can start from FF, where it's like the topmost of 64 kilobytes of the memory, where there is only 256 bytes. So how on earth is that possible? So if anyone knows this, please kindly let me know, because I'm getting overwhelmed and I have no idea why is this actually happening. But anyway, let's get back to this documentation. So these addresses contain the address of the reset routine, the IRQISR interrupt service routine, and the non-maskable interrupt service routine. Well, for me personally, all this hardware stuff like this, non-maskable interrupt and kind of like maskable interrupt is a bit of a rocket science. But here is an interesting thing that I'd like to share, because, well, for me personally, it's a very important thing, and at very least that's the reason of why that guy in the commentaries was pissed off so much. So so we were interested in this one. So when 6502 reset input gets pulled low and then brought back high, well, I'm not sure, but I believe this is something electrical that happens with the processor, but I might be horribly wrong. So the 6502 starts its reset process and gets the address to start executing program instructions from this FFFC and to FFFD. Notice that it doesn't start executing at this address FFFC, but reads it to get beginning address of the routine where it should start executing. And this is the very gist of what I was trying to tell you guys. So the implementation by David that I've been mentioning earlier in this video actually did put the program counter to this exact location in random access memory, not in ROM but in RAM, right? And it did put the program there. And then it happened that it was when he actually was trying to run some real world 6502 programs, they didn't work. And probably this is the reason, because this is the address to look for a byte value that we need to put the program counter to in order to start executing program from there. So this is kind of like a pointer. It's not the value, it's just a pointer. I would like, yeah, so this is a pointer. So this is the memory address containing another memory address that is actual place or where to start the execution from. So yeah, so it reads, it doesn't start executing at this address, but reads it reads this address to get the beginning address of the routine where it should start executing. That routine will normally have to be in RAM. And well, if this is so, then probably, then if this is so, then probably that routine should be somewhere in this system monitor. I think this should be somewhere in here. But when I was looking for the constants of FFFC, I didn't actually find any. But so here they kind of defined here, but this reset FFFC just defined. But actually, hold on a sec. Doesn't this FF mean the exact? Hold on a sec, guys. Oh my god, did I just find the answer for my question? So if it takes FF, well, but hold on a sec. If FF is the address in the random access memory, then it would override the stack, because yeah, this is a bit strange. Or if only Apple One did have a stack in a somewhat a different place, potentially. So yeah, anyway, let me just read a few words about the stack as well, because that's another interesting thing. Not sure where the stack stuff is. So let me just try to search for that quickly. Stack, okay. Oh yeah, here it is. So please know that it's almost imperative that you have at least some RAM in page 0. So this is not as the 0 page, and page 1. Yeah, this is very important. So starting from 100 hexadecimal to 1FF hexadecimal, and this space does not have to be 100% RAM, but virtually all applications will need at least some RAM in each of these pages. And here is the explanation. So occasionally we see someone new in the forum who delays adding RAM to his project, thinking he doesn't need any variables yet, but then he has the subroutines or tries to have things on the stack or has an interrupt, and it doesn't work because the stack requires page 1 of the RAM. So from 100 hexadecimal to 1FF hexadecimal, right? We know stack memory can't use this stack related instructions and interrupts, and yeah, transfer in stack pointer to X, and the value of the X registers to stack pointer will be pretty pointless as well. So page 0, also known as the 0 page, abbreviated ZP, occupying the addresses from the first 256 bytes literally. It used for sure single byte addressing, but more importantly, 0 page is in a sense 256 8-bit processor registers. Yeah, so that's another thing that is mentioned in many places. So it's meant to be used, it's meant to compensate the lack of registers in 6502. The pre-index and post-index and direct addressing modes available. Okay, so yeah, by the way, only available. Yeah, I'll need to read through this as well. But anyway, yeah, here is the part in the regards to sex. As for page 1, so address range from 100 hexadecimal to 1FF hexadecimal. The reason for the need of at least some RAM in page 1 is that 6502 uses this page for its hardware stack. So this is the hardware mapping for a stack. So stack should be, so stack pointer, the value of the stack pointer register is FF initially, but we need to add the offset of this 100s to it, and it grows downwards. So from 1FF, so if you just push a single element to stack, this would be 1FE. If you push another element, this would be 1FD, then 1FC, 1FB, 1FA, and so on. So the stack grows downwards. So this, yeah, so this, the page 1 of so-called page 1 of random access memory is used for a stack. So it's a little bit unclear to me of why. So so if they say that the 6502 processor actually takes, if it takes the value of where to put this his program counter to in this bit in the ROM, in the read-only memory. So if this is FF, then it actually, the next, so this is the very last byte of the 0 pages, right? And the next byte after it is going to be already the stack territory. So does it mean that it overlaps the stack or what? So this is a very unclear thing. Or did they put the stack in Apple One not to from 100 hexadecimal to 1FF hexadecimal, maybe to somewhat a different place? I don't know that as well. But anyway, so, well, obviously, as far as I'm not looking for compatibility with the Apple One actually, and with whatever other kind of like, with whatever other retro software for retro computers, I can actually put, I can put the stack wherever I want, and I can put the program counter wherever I want as well. I can even avoid having a ROM, and I can even avoid having those, I can avoid having this interrupts and all this stuff, because I don't need to emulate that sort of a thing. So just to give you an idea, for instance, in this brilliant JavaScript simulator, not the emulator, but the simulator, doesn't seem that we have things like that at all. And here the stack actually has just it's not mentioned here. Well, actually, yeah, probably the stack is just the page 1 as it was. But the program counter, yeah, it's like the program counter actually starts from. So if we just reset this, it starts from 600 hexadecimal. So this might be the case to consider. Basically, I think kind of like why not, basically, right? So it's just seems to be just fine. But anyway, so yeah, that's all about it. So I'm not sure how exactly am I going to be implementing this at this point, but well, anyway, I think that at least being aware of this information presented here in the documentation, it's at least useful. And you know, like if I'm about to be breaking some physical kind of like, I know, laws of how this processor works, then at very least I would be aware of what exactly am I breaking and why. So just to justify this, not just because of total unawareness, but just making this intentionally. That's what I wanted to say. So yeah, and okay guys, so the very last thing is the actual demonstration of what did I came up with so far. So the current project, right? So here I have the memory map. So the memory map of in the 16-bit real mode. So this I call it 6502 M6502 OS. It just quirky way to replace the letters of MOS 6502 because OS serves like operating system. So don't get confused by this name. So it's actually meant like MOS 6502, but written in a bit different way to say that this is the operating system. This is not the real processor. So it like references to the fact that it's more like a simulator rather than the emulator of somewhat a real thing. So I just want to talk to this using the 6502 machine codes and get them executed. That's all I want. I'm not going for backward compatibility with Apple One or whatever. So anyway, here, well, so this is specific to x86 machines architectures. So 7C00 is where traditionally the bootloader code runs. So initially the instruction pointer of x86 points here. We just execute the bootloader. The bootloader loads some additional things. So for instance, this one. I've separated the global procedures, and now it's very cool how we can use them using the FARC. I'll demonstrate this just right in a moment. Then the CPU simulators itself, and then this 8 kilobytes of the emulated RAM. And here I already have the memory map for that emulated RAM. So whatever happens with this 8 kilobytes, it should be represented here. So far I've done this like I've specified the 0 pages and the stack memory, and again, like where the program to execute is actually gibberish, so we don't need this really. So it's where the program counter is still really unclear. And here I have the layout of how my files are located on the USB flash drive. So when I'm gonna be writing this to the flash drive and then running on real hardware, also in the emulator as well, in x86 emulator in this case. All right, so probably let's start with the procedures. So the previous implementation of Game OS, the operating system I've been introducing at the beginning of this video, had a problem that things like clearing screen, printing strings, sometimes printing the hex numbers and setting attributes, etc., was getting from one file to another all of the time, causing lots of duplications, which I really wanted to avoid in this case. So all the functions that would be globally called from different parts of my code, I decided to put them into a single place in the random access memory, and then just using the var jumps, which gives like a segment plus the offset address, which allows to call this from whatever in the entire 640 kilobytes of the random access memory available in a 16-bit real mode on x86 architecture. So and just to get back, it uses the return var instead of return, and the way I call it, it's just first the segment. So procedures is the address of where it's, well, actually it's not even it's not even a segment, it's actually the real address, and then the local offset of the function. So this clear screen, for instance, so it's just 4 bytes after the beginning of the file. So we have, so here this instruction takes exactly 4 bytes, and then and it runs in 7E00. I'm just initializing by putting the code segment into AX, then initializing the DS, the data segment, just to hook up the variables here. And actually, I can then call like procedures. So to run procedures clear screen, I just need to say 7E00 and then 0004, which is this local offset, so 4 bytes offset, and then we have this clear screen. Then we have, for instance, oh my god, where is that? 16 bytes offset, and there, then the print string start, then the print hex number, and so on. So just to be able to use these functions from wherever of my code. And here is the file where the actual CPU simulator is going to live. So what I've done so far is just define the register. So register A, X, Y, program. This register P is actually processor flags. So we have, oh man, what have I done? Nope. So we have this kind of like negative, overflow, reserved, break, decimal, interrupt, 0, and carry flags, right? Which are specific to 6502. And stack pointer points to FF, but there would be the offset of 100 hexadecimal added to that to point to the actual memory location, because the stack pointer, unlike the program counter, only 8-bit, so it just can't hold the real physical address. We just need some offset to be added to that. And the program counter, well, this is run actually, so I will just initialize this to 0 for now, because yeah, the FFFC is the place of where to look for a byte of where the program counter should point to, and not the place where it starts, where the program starts from, which was the case in that tutorial I've been mentioning. So yeah, I didn't yet create the execute function or something, so it's very, very basic, but I just want to show you the very initial thing that I have. So I'm currently only capable of printing this predefined strings, so I can say call. And now notice how cool it looks. So it's almost like object-oriented C++. Actually, it's not an object that represents the method. No, it's just the kind of global address followed by the local offset. So procedures and print screen. So just define this handy shortcuts. So print string, and this should print now hello. So nothing special. It doesn't print hello because it's undefined, so I just made some sort of procedures in plural. Okay, so yeah, here it is. And by the way, note that we have not 80 by 25 characters, but instead 40 by 25. Well, actually, the original Apple one seems like it had 40 by 24. But, well, I think that 40 by 25 is not that bad at all as well. And it also looks very, very nicely on the real hardware as well. It's actually, CAM is very accurately emulating how it looks on the real hardware. And also, like the cursor is actually the square and not like this thin width and thick height. So it's really better for if I'm going to be coding some games. So the tiles would be like squares and not like this, but just like all like the squares, right? Okay, and also so before anything else, I would probably create a comfortable development environment. So I've already prepared the function for that. So just to print, so there would be lots of extensive debugging. So I will need to examine every single part of the random access memory. Both kind of like the one I work with here in this simulator and the simulated memory as well. So if say I want to type the hexadecimal value, so 0A for instance, so I only print the nibbles now, so now don't just print the nibbles. So if I say call procedures and print hex. So it doesn't print an entire byte, even it just prints a single nibble for now. But anyway, well, it doesn't even do that. So what did I do wrong? Print hex. What did I do wrong, guys? I'm sorry. Just procedures, print hex. I don't know. I swear it did work before I started. Yeah, it prints 9. Okay, but why it doesn't print the A? Should be. Oh, now it works. I know something was horribly wrong there. So so you see, like what it does, it actually converts the. So it prints the least significant nibble in this byte, which is stored into AL. So this A, this is the hexadecimal A, which is 10 in decimal. It's turned into the ASCII character A. So that's how I can print all this memory maps in hexadecimals. It's not implemented yet. Once I do that, I will probably make a video demonstration on that as well. So yeah, so I'm gonna be able, so like every so in the debug mode, whatever instruction gets executed by the processor, so that would be giant, well, it won't be a switch case because we don't have switch case in assembly, but compare with a single constant, comparing like the value that we've just read from the memory with a single constant, and depending on what we have there would be like functions to execute LDA, like load the A register in immediate mode, in zero page addressing mode, in absolute, in offsets, and so on. So literally all we have there based on the certain opcode that is going to be there. So generally, this is the very last thing I want to say, and we'll end this video. So generally, what this simulator is going to be all about. It would be taking 6502 machine codes as an input, and it would be executing them in this virtual environment as the output. So by saying virtual environment, I mean this simulated random access memory for this kind of like imaginary computer that I'm building. And yeah, by the way, I just want to end this video with a little joke. So the benefits of having the software implementation of thing that doesn't exist in the real world, say now I have only 8 kilobytes of random access memory, but if I want to add some random access memory, if I want to increase the number, all I need to do is just to change this number in the memory map.txt and nothing else, because this is just an abstraction. So literally starting from here, we have really lots of memory. So not exactly 640 kilobytes as that's the entire number of memory, but at least I believe 600 kilobytes. Yeah, that's we really have lots of memory there. Anyway, so it doesn't really have the upper limit. So this is just for me to like have some borders to think within, but on the real deal, this may be whatever. And actually, it's only limited by the amount of memory left there by the 16-bit x86 real mode environment. Okay, guys, so this is pretty much all it from my side in regards to this project. So I don't know, probably you will think that I'm crazy and why the heck to do this, but I'm very addicted to this thing, and it's very interesting for me personally, and I really want to make it work one day. For those purists and perfectionists who might be potentially watching this video, so please excuse the fact that I'm not doing a real emulator, because things like emulating the clock ticks and try and make this 1 megahertz like frequency for the processor and things like this are a little bit too overwhelming and a bit of a rocket science to me, because again I'm complete noob in electronics. And all I can do is actually to trying to write this simple program that takes 6502 machine codes as an input and does something with this actually 16-bit x86 environment, does something with that as the output. So this is going to be happening in the simulated environment within this random access memory. And then I will also need to think of how in particular am I gonna be doing things like so how would I implement the fact of printing characters, let's say, to screen from the 6502, because in x86 obviously I can either directly write to the video memory, or I can use the BIOS interrupts, like interrupt hexadecimal 10, for instance, and then specify the character attribute. Well, it's not going to be changed, but anyway, the character attribute and the character itself, basically, right? So I'm not sure how exactly am I going to be doing that. Well, maybe this Apple One manual would help me. So it says so maybe somewhere here. So I would put it. So I'll need to study this code extensively in order to figure out what the assembly code meant to be. So what it meant to happen, or when. So how the printing actually is done in 6502 assembly in Apple One, and then I will try to mimic that, and hopefully, well, potentially that would give at least, maybe not the 100% compatibility, but at least some sort of a compatibility, like to at very least being able to run some applications like maybe like this one, right? So maybe like just literally just printing the characters from the predefined source. That's pretty much all about it. Okay, yeah, so this is it from my side. I hope you've enjoyed the video, and again, I'm not going to be doing tutorials because I have no idea whether I succeed or not, so I can't just making that tutorials, but I'm going to be making this like development progress videos that fortunately, which hopefully would be instructive, informative, and just giving some ideas of how things work. Maybe it would be interesting to someone, maybe not. I don't know, but well, I'm doing this for my own self, and well, for some reason, I don't know. I feel this is very, very interesting to do, and yeah, that's just my own personal thing. But maybe just someone would be interested in this as well. Okay, guys. So yeah, this is it from my side. So thanks for watching. Until the next time, and take care.